In the previous lectures, we had seen about the vector fields, and from vector fields, how can we conclude about the stability of the equilibrium points. And then we also saw that the slopes, in case of a one-dimensional system, the slope of fx around the equilibrium point can also be linked to the stability of the equilibrium point, and then it was extended to a higher dimensional system where essentially it was finding out the Jacobian of the function f of x and at the equilibrium point and evaluating its eigenvalues to conclude about the stability of the equilibrium point. This is what we call as the linearization. So the next question that we now the question that we will raise is, suppose you have a system, autonomous system, which is given as this, with x of t belonging to Rn, uh, x of 0 being some thing like this belonging to Rn. F is a map from Rn till Rn. Okay. So the question that we ask is, under what conditions will a solution exist and will be unique? Okay, that too at least in a time interval 0 to delta. Okay, so we are questioning the existence of solution and uniqueness of a solution in a certain time interval 0 to delta. So what is the time interval within which a solution will exist, and that solution will also be unique, given that the differential equation that we have, or the system that we have, is of the form x dot equal to f of x, and initial condition being at x0. Okay, when we talk of this, essentially, if f is differentiable, then solutions exist and are unique. Okay, so differentiability of f ensures that solution exists and are unique. Also, if f is continuous, okay, so the continuity of the function f is, or rather I can say, the continuity of f guarantees the existence of a solution in a certain time interval. Okay, that is the existence of solution in some time interval. So the delta will also depend on the continuity, 0 to delta, where delta is some number between 0 to infinity. Okay, so if f is continuous, that a continuous where continuous at x0. Okay, then it guarantees the existence of a solution. At least one solution will definitely exist in a certain time interval, 0 to delta. Now if f is differentiable at x0, then the solutions will definitely exist because differentiable f is continuous, and in addition to that they will be unique. Okay, so it looks like this kind of answers the question that we raised, that what conditions will a solution exist and when will it be unique over a time interval, right? So f needs to be differentiable. But the question is, so to further um, add, what we are essentially looking for is there a condition that is stronger than continuity but weaker than differentiability. Okay, such that the existence and uniqueness of a solution is guaranteed. Okay, so we are looking for something which is going to be stronger than continuity, because we know that continuity guarantees existence but it does not guarantee uniqueness. So the condition has to be a little more than continuity. It should ask a little more than continuity from the function. But the main thing is, can we have a condition that is not asking the function to be differentiable? I mean, the function need not be differentiable but satisfies something weaker than differentiability. Okay, and yet ensuring that there will exist a unique solution given the initial condition in hand. Okay, so this brings us to something known as Lipschitz continuity. Okay, so what do you mean by Lipschitz continuity? Suppose f is a map from n dimensional real vector to a n dimensional real vector Rn to Rn. So we call this function to be locally Lipschitz. We is called to be locally Lipschitz. So when we talk of locally Lipschitz, then we are talking of Lipschitz of x at a particular point at some point x0 in Rn. Okay, we call this locally Lipschitz if certain conditions are satisfied. If there exists, so the symbol is there exists. Okay, there exists what? Number one, a neighborhood of x naught Okay, with epsilon greater than 0. So you should have a neighborhood epsilon greater than 0 and a finite positive constant L. That is, L will be greater than 0 but less than infinity. Some finite positive constant L. So these two things should exist such that some relationship has to be satisfied. Now, what is that relationship? Such that f of x minus f of y is less than equal to, so the norm of f of x minus f of y is less than equal to L times the norm of x minus y. Okay, and this should happen for all x y in the set or in the neighborhood that we had defined. Just this for all points, not just some choice of x and y from the set. It should be true for any x and y you take in this particular set bx naught epsilon. Okay, in the neighborhood of x naught. So what it is essentially saying is this inequality that you see here, norm of fx minus fy should be less than equal to L times norm of x minus y. This should be satisfied for all xy in a neighborhood. So I should be able to find one such neighborhood for the point x naught under consideration, around which local Lipschitz condition is being checked. So I should be able to find one such neighborhood at least, where this inequality will be satisfied for one positive constant L that will hold for the entire neighborhood that I have chosen. Okay, so you see here the x and y keep on changing, but the L, the finite positive constant L that you have chosen to define the inequality, that is constant as far as the given neighborhood is concerned. If you change the neighborhood, the L will also change. Okay, but once you fix a neighborhood, it's the same L for which this inequality has to be satisfied for all pair of points that you can have in the neighborhood B. So how is this set B defined? This is also known as a ball around the point x naught with a radius of epsilon. So the definition is x all points in Rn such that norm of x minus x naught is less than epsilon. Okay. In some cases, people also take a closed ball wherein they will have a less than equal to epsilon. Less than epsilon will do the job. So what you see here, that this neighborhood that you have taken is essentially a subset of Rn. Okay, and the constant L that you have encountered is known as the Lipschitz constant. Okay, and note that this Lipschitz constant that you have for a given neighborhood is not unique. Okay, so the Lipschitz constant that you have for a neighborhood is essentially not unique. There are infinite number of Lipschitz constants that will also work. Why? Because let's say some Lipschitz constant L works for the neighborhood that you have chosen, then you take any positive constant that is greater than this L, that will also serve as a Lipschitz constant because it will satisfy the inequality. What I'm trying to say is, if suppose L is 5, okay, then this, let's say you have a L is 5, so I'm seeing that my inequality here is being satisfied when L is put as 5. Then that essentially means that my inequality will also get satisfied when I choose my L to be equal to 6. Right. So the Lipschitz constant can be 5, can be 6. Okay. If you choose 6, probably certain conditions will become more conservative. But what you see is, for a given neighborhood, this, whether it is 5 or 6, I mean, it can take any number which is greater than 5 in this particular case. Right. So the Lipschitz constant is not unique for a given set. Now, the Lipschitz constant that you have, as I am saying, it depends on the neighborhood, and the neighborhood is defined as far as, I mean, dependent neighborhood is defined with respect to x naught, where the Lipschitz continuity is being checked, and the radius epsilon. So the L here depends on the point around which the Lipschitz continuity is being checked and the size of the neighborhood that is under consideration. Okay, so L depends on this x0 and epsilon in general. Now, to understand what this condition essentially is trying to say, what we'll do is we'll examine one-dimensional systems, because that gives us a better visualization. Okay, so let us take an example for a one-dimensional system. Now, suppose f of x is equal to 4 times x. Okay, x belonging to Rn. Now, if we sketch the curve, what do we get? So this is the f of x axis, and this is, let's say, the x axis, x and f of x. For 4x, it essentially means a line passing through the origin with a slope of x. So this point here is the origin. So the line passing through it is this. Okay, so this is what f of x looks like. Now, let's say that your x0 that you have chosen to examine the Lipschitz continuity is 1. And it is possibly this point, let's say. Okay, and the epsilon, let's say, that you choose to examine this is 0.5. So all points within 0.5 to 1.5 need to be examined, right? So the condition that we have has to be examined. Now the value of fx corresponding to zero point 0.5 is suppose somewhere here, and I think I have to shrink the figure to account for the space for zero point 0.5. So let us consider even a smaller ball so that I can account for this. Suppose 0.8 to 1.2 with epsilon being taken as 0.2. Okay. So what you see here is for the chosen set of zero point 0.8 to zero point 0.2. So the ball here is going to be the set 0.8 to 1.2. Okay. So for all these points, the fx will uh, take values between these two limits. Okay, great. Now you take any point x and y. Okay, choose any point x and y that you want to choose. So let's say that you choose this as the point x, and let's say this as the point y. So correspondingly, the value that you will have for fx is this, and for fy somewhere here, somewhere possibly here will be for fy, and let's say that it is this. Okay, now what is mod of fx minus fy by mod of x minus y? If you see, this is nothing but the slope of the line here, which is 4 in this particular case. And slope is what? Is essentially tells you the rate at which, I mean, it gives you an idea about the rate at which the function f is growing about a particular, in the neighborhood of a particular point. Okay, this is for some xy that I chose. Now you choose any xy in this range. For this particular example, what will happen is for all xy in the set 0.8 to 1.2, your L will turn out to be 4. Okay, so L is at least 4. So in fact, I should say L is less than equal to 4. If you choose 4, then norm of x minus norm of y, which is mod in this case, will be equal to 4 times x minus y. Okay. So what you see here is this particular guy around the point 1 in the ball. This is essentially satisfying the relationship that we need to have the Lipschitz continuity. Okay, for x naught equal to 1, epsilon equal to 0.2, and L for any value of L that lies within this particular set. So the function f is Lipschitz about the point 1. So I am able to find at least one neighborhood where this is being satisfied. Okay. For that one neighborhood, if I can show that it satisfies the inequality, then I'm done. If there exists a neighborhood in which it satisfies the Lipschitz continuity inequality, then the f is Lipschitz. Okay, now let us see if we can take up one more example. Suppose f of x is, let's say, e power x. X belongs to Rn. Okay, so let us first consider x square. We'll go to e power x later. So this is the axis for f of x. This is the axis for, let's say, x. And x square would roughly look like this, with this being the origin for the axis that has been set up. And now let's say that we want to check the Lipschitz continuity of f of x around, let's say, this particular point, which is 1. So for this we'll take a neighborhood with epsilon to be 0.2, which is the following. Now the range in which fx can vary is essentially this. Okay, so suppose I take x here and a point y here. So note that the x naught that I'm interested in is 1. Epsilon that I have chosen to check is 0.2. And so the ball that we are going to get is essentially the set 0.8 to 1.2. Now you see here, suppose the fx takes this value as per the location of x, and fy takes this value as per the location of fy. So when you do calculate this f of x minus f of y norm, which is, because it's a one dimensional, it can be taken as mod by x minus y. You are essentially calculating a slope. Okay, so let's say that this becomes equal to some finite positive value L. Okay, now instead of this, let's say that you choose points which are very close to 1.2. If this xy are closer to 1.2, then what happens? Because you are allowed to choose any pair of points in the set 0.8 to 1.2. If xy is close to 1.2, then this L will be even higher. So what is the maximum value of L that you can have? The maximum value of L that you can have for the set that you have here will essentially occur for this particular case at the boundary point 1.2. So the slope L would be highest here. So the Lipschitz constant L in this case has to be greater than equal to d by dx of x square evaluated at x equal to 1.2, which gives me 2.4. So the Lipschitz constant is minimum 2.4, and maximum can be anything but finite number. So if you choose L to be at least 2.4, then the inequality of norm of fx minus xy being uh, less than equal to L times of norm of x minus y will be satisfied. Okay, for this, for any value of L satisfying this will be satisfied, right? So similarly, now let's say that you want to consider Lipschitz continuity at x equal to 0. So a similar thing will happen for Lipschitz continuity when when you check for Lipschitz continuity when x0 is on the right hand side. Okay. Now suppose you want to see what happens at how do you check the Lipschitz continuity at x equal to 0? For this, again, we'll choose uh, epsilon to be, let's say, zero point 0.5. So which means the ball would basically be minus zero point 0.5 to plus 0.5. Okay, so let's say that this is 0 0.5 and this is minus 0 0.5. Okay, so this is the range within which you can check. So what you can do is just take any xy in this set. So let's say that I choose my x to be here, and which will have fx landing up somewhere here, and I choose my y to be at this point with my fy possibly landing at this particular value. So then fx minus fy by norm of x minus y, here you can observe that this is going to be less than equal to L, where L is going to be greater than equal to d by dx of course x square, the function under consideration, evaluated at x equal to 0.5 or x equal to minus 0.5, because both of them will have. And okay, you have to take the positive of it. That is what the L would be. So in fact here also, when I evaluate it, I have to take the mod of the value. Okay, so the two, in these cases, the two extreme points that you take accordingly, uh, you'll have the slope calculus. So this will possibly be 1, which means that the Lipschitz continuity condition around the point x equal to 0 for the radius of zero point 0.5 will be satisfied for all points in the neighborhood if L is chosen to be greater than equal to 1 and a finite number, because the finite number requirement comes from the definition of Lipschitz constant. Okay, so F is essentially Lipschitz about x0 equal to 0. Similarly, we also saw that F is Lipschitz about the point x0 equal to 1. Now notice that when the a value of x0 changed and the value of epsilon changed, so when the set and which is being considered changed, the L value also changes, right? Okay, now if in let's say this case itself, if we choose epsilon 1 to be equal to 0.6, okay, then in such case the L would turn out to be greater than equal to 1.2, and the condition changes. L has to be greater than equal to 1.2 and a finite number. So if even if you have the same point under consideration for the examination of Lipschitz continuity, if epsilon changes, so here I have taken a new epsilon, so means the set under consideration changes, then the Lipschitz constant that is applicable for the set also changes. Okay, so Lipschitz constant even for a given point under consideration is not unique. It changes. It changes with the change in the set. Okay, so if the set size decrease, possibly the Lipschitz constant will decrease. If the set size increases, possibly it will increase. In some cases, the reverse happens. In some cases, the L won't. I mean, the minimum L that you would require won't change. Okay, so it is dependent on what is the function that you are actually studying. If you have f of x to be equal to, let's say, e power x with x belonging to Rn, then again, in such a case, if you plot f of x with x, let's say that this is the graph, and let's say this is the origin. Similarly, if you want to check Lipschitz continuity, let's say about the point 1, and you choose the ball to be sorry, let's say you choose the ball to be 0 to 2, which is essentially this point. Okay, so the point of interest is x0 equal to 1. The radius of the ball that you have chosen is 1, which means the neighborhood in which you will be testing this is essentially going to be 0 to 2. Okay, so what you see here is, if L is a finite positive constant, of course, but chosen to be greater than d by dx of e power x evaluated at x equal to 2, which is basically going to be e squared. Okay, if this is the case, then for such a L, so L lying between e squared to infinity but not actually taking infinity, so it's a finite constant. For such L's, we see that in this neighborhood, for all points fx fy, the Lipschitz inequality which we have is satisfied for any L that you take between these values. Okay, similarly you can evaluate for slopes when around 0. So let's say that I mean, if the point of interest is 0 and the epsilon is chosen to be, let's say, 1, then the ball here becomes uh, the neighborhood that you will be seeing, or the ball around x0 will be basically -1 to +1. And in this case, you will basically have Lipschitz constant to be more than, I should say, evaluated at this e power x. Okay, so which means if you choose your L to be more than e but less than infinity, then the Lipschitz inequality that we had will be satisfied for all the points in the chosen ball. Okay, so e power x is also Lipschitz in this particular set. Sorry, in this about this particular point x0 equal to 0. Okay, so it is, we call that it is locally Lipschitz because we are evaluating at one particular point. Similarly, if you have let's say f of x to be equal to e power minus x with x belonging to Rn, then in such cases you can again evaluate and see that for x0 and epsilon as 1, the ball that you will be examining is going to be -1 to +1, and f of x will be Lipschitz at the point 0 when L is chosen to be in this particular range. Okay, which is essentially, so if L is chosen like this, then the Lipschitz inequality that we have is satisfied for all points in this particular ball. Okay, so f of x is essentially Lipschitz at the point 0. So what you see here is basically the Lipschitz inequality is kind of trying to restrict the uh, growth of the rate at which the function will grow with respect to the change in x. Okay, so what it is trying to say is a function is locally Lipschitz around a point x naught if you can find a set which you can tell it to be a neighborhood of that x naught, wherein in that particular neighborhood the rate at which f changes with respect to the change in x in that particular set is upper bounded by a finite positive constant. That is what it essentially means. So for even n dimensional system, this notion will follow. Okay. So fx minus fy, the norm of fx minus fy denotes what? Is basically tells you how big, I mean, how far away fy is from fx. And x minus y norm tells you how far is y from x. So what this inequality is trying to say is, if you go, if the distance between x and y increases by this much, then the distance between fx and fy cannot increase beyond this particular value. Okay, which is essentially again reiterating that it is restricting the rate at which fx can the norm of f, I mean this growth of f gets restricted. It restricts that growth of f. Okay, so this is what is known as local ellipses. Now, uh, so what we have here is, if fx is Lipschitz at a point x naught in, let's say, a domain D which is a subset of Rn, then we say that fx is locally Lipschitz at that particular point. Now, if fx is let's say locally Lipschitz at all points in a set D which is a subset of Rn. Okay, now when we say locally Lipschitz at all point in a set D, that essentially means if you choose a point, let's say alpha in the domain, then the corresponding Lipschitz constant will be L alpha. And if you choose a point beta in the domain, the corresponding Lipschitz constant will be L beta, but L alpha and L beta will not be the same. Okay, they will be basically different for each point. The reason being, you cannot, uh, which essentially indicates that you cannot find one value of L for which you can restrict the, I mean, which for which f will satisfy the Lipschitz continuity condition in the entire domain. Okay, so in such cases, we call f to be locally Lipschitz on D. Okay, for example, fx equal to e power x is locally Lipschitz on R, right? Why? Because as x at any point x naught that you want to check Lipschitz, then you will see that f of x is Lipschitz, but you cannot find one Lipschitz constant L that will act as a Lipschitz constant for all the points on the real line. Okay, that cannot be done, because you choose a L, fix it, then you change the point, you will see that that L won't hold and a higher L would be required. Okay, higher Lipschitz constant would be required so as to act as a upper bound, and this keeps on happening. You keep on finding point, this will keep on happening, so you cannot find a particular L. So f is locally Lipschitz. If fx is locally Lipschitz on D and there exists one Lipschitz constant L for the domain or the set D, then we say is, what we say is f is Lipschitz on D. Okay, example, f of x is e power x for D in the range of, let's say, 0 to 10. So here any L that is greater than e power 10 will actually act as a Lipschitz constant for this function in the domain 0 to 10, right? So that is why I can say that in the domain D the function f is Lipschitz. The function f is Lipschitz on the domain D given here. Last is fx is Lipschitz on D and the domain is essentially the entire Rn. Okay, which essentially means fx is Lipschitz on Rn, the entire space. Then we say that this is globally Lipschitz. Example of globally Lipschitz functions: fx is tan hyperbolic x and the domain chosen is Rn. Okay, answer D equal to Rn. So fx is essentially Lipschitz in the domain Rn, and in fact what you will see is the choice being any L greater than equal to 1. For any L greater than equal to 1 on this entire domain, f of x would be essentially Lipschitz. So we call f of x to be globally Lipschitz. Correct. Okay, so what we saw here today is the definition of Lipschitz continuity, a few examples from one-dimensional systems so as to understand what Lipschitz continuity means. Then what does it mean for higher dimensional systems, and we also saw the variations in the way f is Lipschitz depending on the existence of the existence of a Lipschitz constant either for the entire set D, which is a subset of Rn, or for the case when D is the entire Rn, or for the case when you have f to be Lipschitz at all points, but not a single constant can act as a Lipschitz constant for the entire set. So the first case where we'll evaluate Lipschitz continuity at just a single point, we say that f is locally Lipschitz at that point. Now if f is locally Lipschitz at all points in D, but you do not have a single Lipschitz constant that can upper bound act as upper bound for all points, or as act as Lipschitz constant for all points in the domain, then we call it to be locally Lipschitz in the set D. Then we saw that if in a set D f is locally Lipschitz, and if you can find a constant L which acts as Lipschitz constants for all the points, then we call f to be Lipschitz on the set D. And if f is Lipschitz on the set D and the D is entire domain under consideration, which is Rn here, then in such a case we can call f to be globally Lipschitz. Okay. So in the next lecture, we'll start our discussion on how Lipschitz continuity will ensure existence and uniqueness, and under what conditions on the function will the so we'll also try to find out the time interval within which the solution will exist and will be unique, and then we'll see under what conditions the solution, if exists, will exist over the entire time interval 0 to infinity and also remain unique. Okay, so we'll stop here. Thank you.